are the big things in the world of physics that we look at. But there's more, and what I want to look at today is the more. So if I could get Rebecca, can you read the introduction here?
In a swimming pool problem, our initial function R of t had units of gallons per minute and represented the rate at which water was leaking from the pool in gallons per minute.
The definite integral of R of t with respect to t?
Yeah,
from t equals 0 to t equals 8.
Yeah. Was used to determine the total number of gallons that leaked from the pool during the time interval t equals 0 to t.
Okay, so I just want to make sure you guys get this in the note in your notes here. So why is it? Why is it that if R of t, what did it represent in that swimming pool problem?
The rate at which water was
Rebecca just read it.
The rate at which water was leaking.
Okay, hold on. I'm hearing two different things. I'm hearing like gallons per hour. That's not what it represents. That's how you measure the function. And I'm hearing the other thing. What did R of t represent?
Rate at which water is leaking from the pool.
Okay, I'm going to say it's how fast water leaked from the pool. Okay, the rate. So R of t was telling you how fast water leaked. How fast water leaked from the pool. Pretty good? Yeah. But the definite integral, when you do the definite integral, what it gives you is not how fast, but how much water leaked from the pool. Leaked from the pool. From t equals 0 to t equals 8. And it's a really important distinction. We're going to do a lot with rate functions, with how fast functions. With velocity, it was how fast are you running? How fast are you riding your bicycle? If you have a rate function, when you do the integral, it becomes a how much. How much water came out of the pool? How far of a distance did you travel? Now the units, you're going to have to pay attention here. The units are always going to come from looking at these two things. What was R of t measured in for the swimming pool? It was measured in gallons per minute, but then I'm multiplying it by the time. What was I measuring the time in? Minutes. And if I look at the units, gallons per minute times minutes has to give me gallons. Are we okay?
Yeah.
This unit analysis and the explanation is huge in all these different settings. We're going to keep coming back to this. So Diego, can you pick it up from here?
In physics, v of t, the velocity is measured of the rate at which the position changes, and integral of a dt with respect to t represents the total change in position from t equals a to t equals b, otherwise known as displacement. If v of t is measured in centimeters per second and time is measured in seconds, then the integral of b of a dt with respect to t would be measured in.
Okay, well let's look at this. We're looking at the integral from a to b of v of t dt. What's v of t being measured in?
The rate at which position changes.
Okay, careful. Here, listen to the question again. What are the units being used to measure v of t?
Centimeters per second.
Centimeters per second. What are the units for the time? Seconds. So what are the units for the integral for the whole thing? Centimeters per second times seconds per minute. It has to be centimeters because the seconds are going to cancel out and we're going to get centimeters. Now for those of you that weren't here yesterday, v of t is a how fast function. It's a how fast is your position changing. Right? I'm like on my bike or I'm running. Gosh, that's going to be so awkward on the video. Whatever it is, if v of t is how fast I'm moving right or how fast I'm moving left, then the integral is going to have to represent how much I have moved. Are we okay? Yeah. It's this constant connection between your rate function is a how fast, but your integral becomes a how much. How much change has occurred. This is where we're focusing today. All the friends are good? All right, Sylvia, can you pick it up from there?
In application problems, the definite integral can be used to determine the total change in a function from one point to another. Armed with this idea, let's consider the following problem. You must pay attention to the units and explain your final answer in terms of the situation being explored.
Excellent, thank you very much. All right, so with that said, Axel, can you read the introduction of the problem here?
A cup of coffee at 90 centimeters Celsius, 90 degrees Celsius is put into a 20 degrees Celsius room where T equals 0. The coffee's temperature is changing at a rate of RT equals negative 7 while per minute where time T is measured in minutes.
Okay, great. Thank you very much. All right, so R of T, I want to make sure they're all on the same page here. What does R of T represent? The rate, be specific, the rate that what's happening?
Temperature is changing.
The rate that the temperature of what is changing?
Coffee.
Of the coffee. It's the rate that the temperature of the coffee is changing. And what else do we know? We know that the cup of coffee, what's the initial temperature?
90 degrees Celsius.
90 degrees Celsius, and it's put into a room at 20 degrees Celsius. Forget about calculus just for a moment. What has to happen to the coffee?
It's getting cold. It has to be cool.
Getting colder? We're cool. Is that what has to happen? Right? You take a cup of coffee, you put it in a room, the coffee's at 90 degrees Celsius, the coffee is going to cool. Are we good?
Yes.
Okay. Does the coffee ever reach 0 degrees?
No.
You don't know? I heard a lot of no's. Think about the situation. The coffee starts at 90 degrees Celsius. The room is 20 degrees Celsius. Does the coffee ever reach 0?
No.
Sylvia, why not?
Because the room is 20, it can't be colder than that.
Right, if you're starting up here at 90 degrees Celsius and you put it in a room at 20 degrees Celsius, the temperature will decrease. But it doesn't decrease like forever. You don't start to form ice on it because the room's at 20 degrees Celsius. And if you think back to chemistry, good times I'm sure, physics, good times for sure, you've got this exchange of energy between the coffee and between the room, and it's this like give-take relationship, kind of like ours. We good? All right, so with that said, see what you can do with part A. And then part B. Okay, I'm just going to do a quick lap through the room. Yep, you can absolutely use a calculator. You don't need a calculator in part A. You have to have a calculator in part B.
Good. In the context of this problem, explain the meaning of the expression integral from 0 to 10 of R of t dt. Looking for perfect answers.
Oh, I haven't read it, so.
That's what I would look at, like, what does this function represent?
Yeah, it's just saying
And
the
then
meaning.
go for the explanation.
Change in temperature.
The rate?
No, because not the rate, that's RT. It's on the
Oh, yeah.
velocity.
No, but it's still
It says the
Haven't seen the perfect sentence yet, although Jackie wants me to check.
Saying how much or how fast it changes.
Yeah, but I thought like in total the whole thing was how much, but like RT is just like
No, think back to the first question.
There's some things in there I really don't like. I'm
it
going to ask you to
depends
repeat
how
this.
fast is it, like the whole thing.
You also didn't include units.
It's the whole thing, right?
I need a fully correct explanation.
How much?
So no, I'm talking about the whole total thing or just like RT? Oh yeah, I'm talking
You
about
also didn't
like
include units.
the RT.
Yeah, RT.
It's supposed to be like how fast, and then the whole thing is how much. Es que no me dejan hablar.
There's some stuff in there that I like, some stuff in there I'm not a big fan of.
Question 106.
This is almost perfect. Can I get you to read this one just?
So it's from 0 to 10. The temperature dropping.
All right, so asked Jackie and I've asked Adrian and did I ask somebody else to read their answer?
Is it me?
No. Jackie, can you read your answer? I want to make sure everybody hears her answer.
I forgot and I started working on my own.
Okay, so what do you have written down so far?
The coffee's temperature is dropping, and then that's it.
Okay, the coffee's temperature is dropping. Is that true?
Yes.
Yes.
That is absolutely true. Is that the fully correct explanation for this definite integral?
No.
Not quite. Adrian, what do you have?
How much the coffee has changed in temperature, degrees Celsius, in 10 minutes.
How much the coffee's temperature has changed in degrees Celsius in 10 minutes? Destiny, what do you have?
I have a question.
You have a question?
Do we, like, do we say dropping or do we say decrease or do we say like what's the changing or?
Okay, hold on. I'll take that question. So dropping and decreasing are equivalent. Changing is ambiguous. Changing could be increasing and changing could be decreasing. Stay away from changing. Changing's not good enough. Okay? So, sorry, Professor Portillo. Okay, so we've got the integral from 0 to 10 of r of t dt. My question for you, what does r of t represent? What is being measured? It's the rate. So give it to me in terms of how fast. How fast? How fast what?
Is the temperature of the coffee decreasing?
How fast the temperature of the coffee is decreasing. Like this is what I'm seeing in my head. Okay, R of t is how fast the temperature of the coffee has decreased. So what does the integral have to represent?
How much?
How much? Give it back to me. This represents how much, okay, how much what? How much the temperature of the coffee has decreased. I like it so far. It's good. It's not good enough though. Hey, you're back. How much the temperature of the coffee has decreased? Sylvia, finish it up.
From time 0 to 10 minutes.
From t equals 0 to t equals 10 minutes. I love it. There's only one thing missing, and my goodness, it is so important in this one.
No, in degrees.
What are the units here, Rebecca?
Celsius.
Degrees Celsius.
Per minute.
Not per
No,
minute.
per minute,
Not per minute. R of t is degrees Celsius per minute. T is minutes, so the units have to be degrees Celsius. Ideally, I'd like to say how much the temperature of the coffee has decreased in degrees Celsius from t equals 0 to t equals 10 minutes. That is the fully correct 100%, you get all the points kind of answer. Now here's the easy, what I think for you guys is going to be the easy part. Part B, using your calculator, determine the exact value of the integral from 0 to 10 r of t dt. That's a like 1 minute or less question. I just want to check in with Gonzalo while you guys are taking out the calculator and doing this. Do you have multiple choice?
Let's go.
You should have They gave me the blue one. That was the free response question.
So that's the rate of
Yeah. All right, and Paul, you're doing it on the calculator back there? There you go. Off the The integral is not rate. The integral is not going to be rate. What happened here? Oh, that's 8:37.
I know.
All right. Can you maybe turn off the light in the front? I'm not sure what's going on here. Wow, that is just impossible to read. I'm not sure what's going on here. Paul, can you test the connection? Okay, according to Paul's calculation, this looks like negative 44.248.
Yes.
Everybody get negative 44.248?
Yes.
So what does that mean? What does that mean?
Jigsaw. That is.
From t equals 0 to t equals 10 minutes, Jose, what happened?
The temperature decreased by 44 degrees Celsius.
Okay, there's a couple things in there I like, a couple things that I don't like. From t equals 0 to t equals 10 minutes, the temperature decreased. The temperature of what?
The temperature.
The coffee, because you also have the temperature of the room that you're dealing with here. The other thing I heard Jose say was decreased by 44 degrees. 44.248. Unless I tell you to round, Jose, don't round. It says round. Jose, thank you for being smart enough to round. I'm moving on now. You had to wait till Mr. Harper came in the room, didn't you? All right, part C. Part C, I'm just going to write it over here. Okay. Part C, brace yourselves. Ooh, that's coming back. Express the definite integral in part B as the sum of an infinite number of rectangles using the right endpoint method. The integral from 0 to 10, r of t dt. I'm looking for you to express this as an infinite number of rectangles. You need to have flashbacks to like before ice apocalypse happened. It's been a while, and this probably isn't a fair question for me to just say, go for it. So, here's what you would have to do. We're doing a sum. We're doing a sum of all the areas. To find the areas, you need two things. Two things. You need to know the width of each rectangle, and you need to know the other piece.
What he's getting at.
You need the width and the height. How wide is each rectangle going to be in this problem? I've got to go from 0 to 10. I have a space of 10. How many rectangles? Not infinitive, that's an English thing. Infinity. There's an infinite number of rectangles. The way we would do it is we'd start with n rectangles. And so each rectangle, because it's going to have equal width, is 10 divided by n. And then you evaluate the function, which in our case is r. Where do I start integrating? I start at 0 plus that width times your counter, that 10 over n times I, or 10 over n times k. Sylvia, did Mr. Madsen just whack you in the knee with the door?
No, I hit myself.
Oh, the first story was at least funny. Okay, so this guy over here is your width, and this guy over here is going to give you the height. Now that's pretty good. You're not 100% done. Why not?
The limit.
You've got a limit. Limit as the number of rectangles approaches infinity. Getting closer. You need to get the counter in there, so we're going from 1 to n, which is the number of rectangles. And I do not need anybody in this room to go any further than that. This is a setup only kind of situation. And all the friends are kind of okay? Diego, what's up?
We could just change. We could put x in for I, right?
You could put x in for I. I want to avoid x because I think of x like x-axis. But if you wanted to use I or k for Karina, you could of course do that.
Then the I and the n are always going to be there.
You're always going to go from I equals 1 to I equals n. The College Board, Karina, I see you, sometimes uses k for the counter. And that just means it's going to be 10 over n times k, but that shouldn't be a big deal.
Oh, like that one problem in the homework.
Like one of the homework problems did that, you know. Oh, and then where does the 0 come from? That's where you start. Right? You're saying on the integral interval 0 to 10, when you do your slicing, all of these are going to be like 0 plus 10 over n, 0 plus 10 over n times 2, 0 plus 10 over n times 3. Karina, sorry.
Do you ever have to like solve it on the test?
In calculus AB, and even in calc BC, you are never going to have to evaluate that. It is a setup, it's a recognition thing only, which should go well.
Yes.
Okay, Sheila and then Rebecca.
So you only need to know like how to set it up with like different variables in different situations.
Yep. Yeah, so like where does the 10 come from? The 10 comes from how long the interval is. 10 divided by n is the width. Why r? Because the function's name is r. Why 0 plus all this stuff? Because you start at 0. Karina.
When you say to start, you know how it says 0, right?
Yep.
Does that only apply to the right one?
And they're generally going to stick with right endpoint method. Because you have to do some wonky things if it's left endpoint or midpoint or whatever. Rebecca.
That's what I was gonna ask, so like, if it's asking a question the right answer method, and my direct one is the trapezoid method, does that matter?
Okay, we'll look at part D. Thanks for moving us forward. Okay, D, using the trapezoid method with 4 trapezoids of equal width, estimate the value of the integral from 0 to 10. So in part D, and I'm going to get out of your way on this, 0 to 10 r of t dt, I want you to estimate this value, not with an infinite number of rectangles, 4 rectangles, 4 trapezoids of equal width. How wide is each trapezoid?
10 over 4.
It's going to be 10 over 4 or 2.5. So like what I would recommend that you do is you start thinking about, okay, like I'm going from 0 to 10, and I'm going to chop it, chop it, chop it. What would each trapezoid look like? What does that setup look like? So take 2 minutes in your group, see what you can do. Paul, as great of a job as you're doing back there, if I can't fix this, I'm going to kick you off. It's not your fault at all, sir. It wasn't plugged in. Alright, Paul, so if you can start doing your calculations over there. It's all working out.
So where do you?
Now it's 4. C and D have nothing to do with Four multiplied by half?
Oh, yeah, I'm trying to have some form
Are you gonna try to pull
So the width.
Alright, for the friends that are struggling with the setup here, we're going from 0 to 2.5 to 5 to 7.5 to 10. Right, because the width is 10 minus 0 divided by 4, which is 2.5. You don't have to draw the trapezoids, but if you do, if you want to, knock yourself out. And then when you make your trapezoids, whatever they look like, each one of them, the formula is 1/2 base 1 plus base 2 times the height. Here's the first base. How long is that?
R0.
This is r of 0, whatever r of 0 is, plus base 2. What's base 2? R of 2.5. 1/2 base 1 plus base 2 times the height. And when we say height, it's weird for the trapezoids, but it's the perpendicular distance between these two. What's that height? 2.5. So your setups are going to look like 1/2 r of 0 plus r of 2.5 times 2.5. And that's your first trapezoid. Okay. Jesus, how are you feeling about the second trapezoid? Could you give me the setup for the second trapezoid?
1/2
1/2
times r of 2.5
r of 2.5
plus r of 5
plus r of 5
times 2.5.
times 2.5. Floor, how are you feeling about the third trapezoid?
It's 1/2
1/2
times r of 5
r of 5
plus r of 7.5
plus r of 7.5
times 2.5.
times 2.5. And oh gosh, who do I want to go with? Diego, tell me about that last trapezoid.
1/2
1/2
r of 7.5
r of 7.5
plus r of 10
times
times 2.5.
times 2.5. That's your setup. Now, are there ways to make this easier?
Yes.
Okay, let's get some hands on this. How could you make this easier on yourself? Henry, what could you do?
You can divide everything by 2.
Okay, you said divide everything by
I mean-
2, which is true. I'm going to look at factoring out that 1/2,
Yeah.
which is fine because everything's getting multiplied by 1/2. What else can we do to make life a little bit easier? Diego, what else?
Right there at the 2.5.
You can factor out that 2.5, so you've got the 1/2 getting multiplied by 2.5. You took out the 1/2, you took out the 2.5 because it's there for all of them. Julissa, what else you got?
Leave the R of 0 again.
R of 0.
And the R of 10.
And the R of 10, okay, I see what you're doing.
And then just multiply 2 times R of 2.5.
Right, R of 0 shows up once, R of 10 shows up once, and all the other ones, double them. So 2 times R of 5, 2 times R of 7.5, and R of 10 is the last one. Anybody get a number on that?
Negative 44.4783.
Negative 44 point, you said 470?
478.
478. Does that seem about right?
Yeah.
It matches, it's pretty close to what we had before, and the units would be?
Degrees of.
They have to be degrees Celsius. Okay. Good. All right, let's see what we can do. I want to push you guys a little bit more. We got 3 parts to go. Maybe you guys get some work time. E, different question. I want you to determine the temperature of the coffee at time t equals 10. I'm going to let you guys talk about this for a little bit. How would you determine the exact temperature of the coffee at time t equals 10? And Paul, if you could show the calculations for us a little bit. Oh, there's going to be calculations.
It's just you. Me here, so.
That's what you think.
Did you bless?
You've been adequate.
Thank you.
Maybe you should
Yeah.
All right, I want to get some hands on this part E. What are the thoughts out there? How are you going to figure out the temperature of the coffee at time t equals 10? Jackie, get me started.
First thing I plugged in 10 to the equation.
So you're doing like that thing? Okay. And Marilyn, what was your idea?
Didn't we already determine how much it's decreasing by from 0 to 10?
How did we figure that out?
By getting the integral part B.
Okay, so we did an integral from 0 to 10 of R of t dt. So you're saying this is the temperature?
No, it's you subtract it from the initial.
Right. What does this represent? This isn't the temperature. What is it?
The change in
But don't use the word change.
the decrease in
It's the decrease in temperature. So if this is the decrease in temperature from time 0 to time 10, how do I get the actual temperature?
subtract it.
And this is where I want to be careful, because I heard you guys just say subtract. Well, subtract from what?
From its initial
90? Okay, so if, go ahead and try that on the calculator. Because most of you guys seem to be going with subtract the value. See what happens on the calculator, and then you'll know what's wrong. Try it on the calculator. 90 minus the integral from 0 to 10.
Oh.
The integral from 0 to 10. On the calculator, you're going to type f1 of x. Jose, what's wrong?
Gives you negative. Yeah, negative 134.
Negative 134? I don't think it gives you negative 134.
Positive.
If you do 90 minus this guy over here, you should be getting positive 134. Why positive 134, which makes no sense? You put a cup of coffee in the room and it gets hotter. Laura, what's wrong?
Whenever you plug it in, it tells you that it decreases by that amount. You don't have to subtract it, you just kind of combine it.
Right, this this value is already telling you a negative value. So what you're going to do is it's going to be 90 plus the definite integral from 0 to 10. And so Paul, if you do that, and the quick way to do that, but yeah, just arrow up, change the 90 minus to 90 plus, 90 plus, and if all goes well, 45.752 degrees Celsius. And we're going to talk about this a lot more next week. This 90 is your initial temperature. This guy over here is your decrease in temperature. And what you're going to get out of it is the final temperature. And we'll talk about it more next week, and it's going to have a fancy name. We're going to call it the fundamental theorem of calculus, but most of you knew what to do even without knowing the name, fundamental theorem of calculus. We all right? All right, keep going, see what you can do.
So that's the answer, 45?
So that would be the answer to the 45.752.
30.
So we don't know.
You don't know the time, yeah.
You just gotta know what it is.
Well, you can do that, but I'm just saying, it's like,
Right, because it's on the
4 plus something.
There's some good stuff happening out there.
30 degrees.
It's just.
That's not a yeah, that's not a
Oh, okay.
Wait, it was 0 to 10.
I see.
Yeah, but you don't know when it's gonna be.
The 10 here was 2. The 20.
Okay, I've got at least 6 different people that have the right setup. Think back to this last one. You started with an initial temperature of 90 degrees. The integral said how much does that temperature change in 10 minutes. The answer when you add the two of them together was the final temperature. What does the 30 degrees represent? It's your final temperature. It's your goal. Your goal is to get 30. Did the initial temperature change?
No.
Still 90 degrees, right? I did not make the coffee colder, warmer, anything like that. So 90 degrees, but my goal at the end is to get to 30 degrees. What has to happen? The temperature has to cool by 60 degrees. Well, how do I figure out how much the temperature is cooled by? How much the temperature is cooled by is your definite integral. You're integrating r of t dt, but what are your limits of integration? 0, because this is where you start integrating. Where do you stop integrating? You stop integrating at whatever this value is. And for right now, I'm going to call it t, and for those of you that the skills are strong, I don't like this. I don't like using a t here and a t here, and we're going to talk about this more next week. Don't worry about it too terribly much. But I want to make sure that we're clear. We get the initial plus the change is going to be the final. We're good? All right, I want to stop here. We've got 6 minutes left. We went as far with this as I needed to, and I feel really good about what's happened. I think we also had some good review. 2 nights homework. It's assignment 78 in the back. Questions 1, 3, 5, and 7. This should not take too terribly long. It's all questions like this where you're pulling the ideas together. Chris, we can turn things off. We've got about 5 minutes left. Here's what I want to do. You can either get started